Good evening, everybody. Thanks for joining us for tonight's advanced spotter training. I'm Brad Carlberg, meteorologist at National Weather Service here in Pueblo. Just letting you know that we'll get started here in a couple minutes. I know it's already 6 o'clock or a minute two here, so we'll just wait another couple minutes to see if there's anybody else that joins a minute or two late here. But bear with us, and we'll get going here shortly. All right, we'll give it about another minute here, and then we'll get started. All right, welcome again, folks. Again, my name is Brad Carlberg. I'm a meteorologist at National Weather Service here in Pueblo. Thanks for joining us for the advanced spotter training. This is the first one of this year and the first online one that we've done. So bear with us. Hopefully, internet cooperates with us tonight, and well, let's get to it. Hopefully, you enjoy it. All right, first of all, a few housekeeping items that we need to go over. If you were in one of our basic classes this year, you had seen this before, but we no longer issue SKYWARN IDs with the mobility of our spotters these days, going out, going away from their homes, that kind of thing. We are decided that we'll no longer issue SKYWARN IDs. If you have one, you're more than welcome to use it. We won't stop you from using it. Hope you do. And use the telephone number on the hail card to call in reports. This way we know you're a trained spotter. In this card, we'll give you access to it at the end of this presentation. If you don't have one already, the number will be the same and all that. In this website here, weather.gov/pub/spotters, will be your access to the hail card as well as your training certificate. And then again, just want to reiterate that we no longer issue SKYWARN IDs starting this year. So a little outline. Some of the stuff we covered in the basic class we'll cover again here, but there will be more meteorological meat that we'll go over. So first thing we'll cover is we'll go talk a little bit about us. Then we'll move on to weather radar and satellite operations, get into more of the nuts and bolts of that. Then we'll get into severe storm and supercell meteorology. And then again, a refresher of how to report to us, which we'll go through that pretty quick when we get to that point. So about us, National Weather Service in Pueblo is one of 122 weather forecast offices across the U.S., as is outlined here on this slide. And there are 13 river forecast centers across the U.S. as well, and these mainly focus on the main rivers throughout the U.S. The CONUS actually, and help us with flood forecasting, that type of thing, especially with snow melt coming up. And a little closer look at the state of Colorado. Our forecast office covers 21 counties in south central and southeastern Colorado. And there are 3 other offices that cover Colorado as well. To the west is Grand Junction. A few counties just to our northeast, Goodland, Kansas office covers a couple of our counties. So we work with these offices quite often, collaborate with our forecasts, as well as warnings to get those messages out to the public. And who we are, there's a number of employees at our office, I believe a total of 22. And there are varying degrees of jobs that we do. The general forecasters like myself, we do the forecasting, and there's also meteorologists in charge, we're getting a new one here in a few months, a warning coordination meteorologist, who actually is also on the line. He's kind of my backup, Greg Hevener, and I forgot to mention this at the beginning, so I apologize. But Greg is on the line as well. And as we go through, no problem, Greg. Sorry about that. But he's here to answer questions as we go through. On the right side of your screen, you should see a bunch of different options. There's an area that you can ask questions, type in questions as we go along. Greg will be there to help answer those questions, or if there's any technical issues that happens on my end, maybe he can jump in and help go from there if there's any issues. And then also at the end, I'll take verbal questions at the end. You'll have the option to raise your hand. There's a little hand that you just click, and the hand goes up to let me know that you have a question. I'll call on you. We'll leave all your mics muted for now. At the end, like I said, if you have questions there that maybe want to go in a little more depth, I can answer those at the end. I'll unmute your mic, call on you, and then you can ask your question, and I can answer that for you as well as the group. So back to who we are. Again, I apologize. I meant to do that right at the beginning. But back to our regularly scheduled program. Next, after the warning coordination meteorologist, we have a science operations officer who makes sure that our forecasts are using scientifically sound processes, keeps us up to date on training, that kind of thing. There's a bunch of support, whether it's administrative, information technology, electronic systems, observation program leader, as well as electronic technicians. And then we also have a service hydrologist who focuses more on the local rivers and streams and that kind of thing. So moving on to what we do. Of course, we keep a continuous weather watch 24 hours a day, 7 days a week. And each office is a little different, but our office, our shifts run 8 a.m. to 4 p.m., 4 p.m. to midnight, and then midnight to 8 a.m. And we have at least 2 meteorologists on staff at all times. So if something's going on, you can always call us. Someone will be there to answer the phone. And not only do we issue general forecasts, but we also issue warnings for tornadoes, severe storms, floods, winter storms, and other hazards as well. Well, for those that live here in southern Colorado, pretty familiar with the threats that we deal with. Severe weather and tornadoes, which is what we're going to be focusing on today, but we also deal with wildfires, flash floods, and river floods, as well as winter storms, which hopefully now that we're getting into late April into May here pretty soon, hopefully won't have too many winter storms left this season. So moving on to weather radar operations. Some things to keep in mind. The meteorologists at the National Weather Service undergo extensive training to accurately interpret the radar information. There are over 70 radar products with each radar volume scan, so about every 3 to 4 minutes, that are used to make a whole warning decision. So it's not just looking at one image quickly and, okay, we're going to issue a severe thunderstorm warning or tornado warning on this particular cell. The information here is just to give you a basic understanding of the radar and what we look at. And you will not be able to make warning decisions based on the completion of this course today. So just keep that in mind. And for those that were in the basic course earlier this year or previous years, probably familiar with this. There are 155 NexRad radars nationwide. Like the meteorologists, they operate 24 hours a day, 7 days a week, 365 days a year. They do a pretty good job of detecting rain and aerosol particles in the atmosphere. However, they do not see the ground. They're aimed upwards a little bit, so they don't see what's actually happening in the ground, and that's where spotters come in with that information, so we can correlate what's happening with the radar with what's happening at the ground. And so during severe weather, we can change how the radar scans, and we can get an update every 1 to 2 minutes. Again, like I said, the radar does not see what's happening right at the ground. So we do need that ground truth. Again, that's where the spotters come in handy. So how does it work? The radar right now, all the radars, National Weather Service radars, are dual polarization. So they send out 2 pulses, a horizontal and vertical pulse. They send it out and then basically listen for it to return if it does, and that tells the radar what's happening out there. And then the dual polarization does help identify what type of hydrometeor is happening out there, whether it's a raindrop, hailstone, snow, graupel, that type of thing. And so we use this obviously this helps us identify what kind of precipitation is occurring out there. And getting a little more in depth with the radar, one thing that we deal with, especially out here in southeastern Colorado, is beam width versus range. Something to keep in mind as the beam travels away from radar, it gets wider and wider. So we're looking at even 60 nautical miles away from the radar beam width is 1 mile from edge to edge. So, and then the further out you go, as you can see on the screen here, 120 miles out, it's 2 miles wide, 180 miles out, 3 miles wide. So you can see, or you can imagine it, it gets very coarse. The amount of data that can come back, it gets very coarse versus more high resolution as it's closer to the radar to let us know exactly what is occurring at that particular location. In that, again, with the beam width, the radar does have a width of slightly less than 1 degree. And as I mentioned before, as it travels away from the radar, it spreads out, gets wider. And these are two of the most important radar characteristics. Covered that. So that means, you know, at 60 nautical miles, when it's approximately 1 mile wide, that means elements within that beam width, 1 mile out, or excuse me, 60 miles out in that mile area, they're averaged. So like the velocities, the reflectivity, that kind of thing, are averaged together. So even though there might be some differences within that mile, it's going to be averaged together to give us an idea what the average is out there. And as I alluded to earlier, the farther out it is, the more and more detail is lost as the farther out we go from the radar. And then plotting the data on a greater resolution map, like a street level map, will lead to inaccuracies because of that distance from the radar will lead to inaccuracies what's actually happening at the ground. So that is why we typically don't show that particular product. And there are a number of different VCPs that we use, which take different slices in the sky. As you can see here, the lowest angle that the radar checks is 1/2 degree, and then all the way up to 19.5 degrees. So we get a pretty good slice of the atmosphere. And then during severe weather, like I mentioned, we get a new scan every 1 to 2 minutes. The radar, it'll be set to do the first 3 scans and then start over again at the bottom, just to give us, because that's the most important part of the storm as far as what's happening at the ground. So we want to see that more often, so it repeats itself sooner. And then on a dry day like today, the radar will let the radar go all the way up to 19.5 degrees before coming back down to 1/2 degree. And what does that look like on radar? And we can put all the slices together and get a cross section. So this is a cross section back in, let's see, 2007, it looks like. And so it gives us an idea not only what the storm looks like from the top view, but the side view as well. So it gives us a little more detail, and we can see what's going on within the storm, not just at the surface or at the lowest level of the storm. So getting into some radar products, one most people are probably familiar with and see on TV all the time, or if you go to our website, we'll see this on the radar. And what this shows is just the energy return to the radar, and the higher reflectivity. In this case, the warmer colors like the reds and purples. I don't see any whites on here, but if there is some whites on here as well, that tells us that it's going to be heavy rain or ice / hail. So it'll tell us where the heavier rain is falling, if it is reaching the ground, and where the lighter rain is falling, if it's hitting the ground at all. So we use this quite often, as you've seen it, like I said, on TV or our website, and those kinds of things. All right, another reflectivity product that we use is called composite reflectivity. Here's another image of base reflectivity. This was down in Alabama earlier this year, I believe. And this I just highlighted this area so you can see the difference. So the difference between base and composite reflectivity is base reflectivity just looks at one particular level, typically the lowest level of the reflectivity of the radar scan. Composite reflectivity will show the highest reflectivity within the entire scan. So if there's, like the last screen I showed, there was a little bit higher reflectivity higher in the storm. This will show that and let us know that there's higher reflectivity somewhere above in the storm. The downside to it is it doesn't tell us exactly where within the storm is that higher reflectivity. Is it at the surface or in the middle part of the storm, lower part of the storm, that kind of thing. It's just all the slices put together looks at the highest radar reflectivity. And then the next thing we look at is velocity, and to get that, the Doppler effect. It's definitely real. If you've ever been near a train track or by the highway and a car is coming towards you and then goes away from you, the sound is different as it changes phases there relative to you. So that's the Doppler effect in a nutshell, and that's how we get our base velocity, which is another important product that we look at. Probably the second most important one. So just some imagery here. This is a storm from last year, the same storm from a few slides ago, over in Kiowa County. So the radar's to the west. So the green colors are away from the radar, and red are actually, that's my mistake. It's backwards. It's completely backwards. I'm so sorry. I don't know what I was thinking, but that's completely backwards. Red is away from the radar. Green is towards the radar. I apologize. I don't know what I was thinking. But anyway, so look at those arrows and flip them around. So one way to remember that is whether it's towards or away from you, is red arrows. Think of it as going away, like you're behind a car with brake lights, are going to be red, of course. So you want that to be, so you know it's going away from you, and then green is towards you. So yeah, so the circulation here would be going in this direction, counterclockwise instead of clockwise. So again, I apologize. Hopefully I didn't make that mistake too many more times.
Hey, Brad, I think I need to go back to a radar school after this class tonight. So
I might have to. Yeah, I might have to. All right, another base velocity example. This one I got right, believe it or not. So this one is just more one directional wind. As you can see here, the greens and blues, the higher values, kind of the bluish color, are going towards the radar. And then once you get east of the radar there, the reds and the oranges showing going away from the radar. So here the winds are pretty strong going from the west to the east. So it just gives you another example of what we can use for issuing warnings and that kind of thing. And another product, velocity product, is called the storm relative motion or storm relative velocity. Both of them mean the same thing. So basically here, we take that base velocity and then we subtract out the average storm motion to give us a little bit better look at certain smaller scale features that might not pop out as much. And this is useful in finding like mesocyclones or tornadic circulations. As we can see here on your left is the base velocity, and then on the right is the storm relative motion or storm relative velocity. And we can even zoomed out a little bit, we can definitely see a little, that circulation there, that smaller circulation pop out a little bit more. So I just, with the same image, I just zoomed in a little bit just so you get a better idea, a little bit better idea of what I'm talking about. And this time I didn't put arrows on it, so I don't think I got this one wrong, but who knows. So another example, the same one from the storm a couple slides ago. This one isn't quite as noticeable as the previous example I just showed, but here again, just kind of highlights the different base velocity versus storm relative motion. Just gives you an idea, helps us look for, especially like tornadic circulations, that kind of thing, real small scale processes that might not show up quite as relevant as on larger scale, the base velocity. And yet one more, and this one's correct too, the arrows are correct on this one too. So here, this one, it just shows a tornadic circulation in Ohio back in 2002, just to give you an idea. Some other products we look at are important products, are precipitation products. This one here, we look at two main ones. This one is a 1 hour precipitation. Kind of gives us an idea of what the rate was for that hour. Any flash flood issues, anything like that might come up because of how much rain has fallen in a relatively short period of time. Again, as you can see, this is Alabama, but it gives you an idea of what we're looking at as far as precipitation falls. And of course, this is a radar estimation, doesn't necessarily mean that's what fell on the ground, but gives us a good idea of what is occurring. And then the other product is the storm total. And this one is we'll calculate or continually add totals up until the storm is over and the precip resets. And these can last for a few hours or maybe even 1 hour up to more than a day. Sometimes prolonged rain events that occur, especially over like the central US, southeast US, where they have a prolonged event. This just gives us a good idea of how much occurred over that particular time. And as you can see in the upper right corner of the image, it tells you the beginning and ending time of that storm total. So now we'll move on to satellite operations. The satellites we typically use are the GOES satellite, which are geostationary. So they basically are in orbit and rotate the same speed as the Earth's rotation. So it's taking a picture of the exact same area all the time, regardless of time of day, that kind of thing. So the two satellites that we use, the GOES East, GOES West. The GOES East was launched in November 2016. GOES West in March of 2018. So they're still pretty new satellites as far as satellites go. We use these to help us identify thunderstorms, tropical storms, wildfires, dust and smoke, as well as fog, depending on the different products that we look at. There's, especially with the newer satellites, there are several products that we look at to help us decipher those different things. And the amazing thing with these, to get that same rotation as the Earth, they are 22,300 miles above the surface, and coming up with some of the images that we have, to me, it's just amazing at how crisp and clear the images really are from that far away. And these are, the images are updated every 15 minutes for the entire domain that they cover, and then 5 minutes over the United States. So every 5 minutes we get a new image that comes in, which is really huge for severe weather operations, that kind of thing. And there's even more so, there are some movable sectors with each satellite that we can request in different areas, and we can get 1 minute imagery with those. So you can imagine how great that will be with 1 minute imagery, seeing certain areas, especially severe weather operations. So here's just a video of some convective initiation over the Palmer Divide. This is the visible satellite imagery. And I'm not entirely sure that you're seeing the full scope of it, but you can see how the detail of the different clouds through the animation that we can see with the satellite. And this is, I believe this is the regular 5 minute interval. Maybe it is the 1 minute interval, but either way, you can see the detail that we can see in the clouds as they move along and develop. Now we are showing you a severe thunderstorm that happened over eastern Colorado. On the left, again, is the visible satellite, and you can see the details of the cloud tops and how turbulent it looks in there. And you can see even the updraft forming and whatnot. And in the right is the IR satellite imagery. This helps us kind of get an idea how tall the clouds are based on the cloud temperature. The cooler the cloud temperature, the taller the clouds are. We can also use especially visible satellite, but other satellite products as well to help us identify where there's fires. Like here's some fires that happened in western Oklahoma back in 2018. So you can see the smoke from the different wildfires shows up pretty clear. I apologize for the small pauses here. I'm coughing in between slides here, so I apologize for the little breaks, but I figure you don't want to hear the coughing over the microphone. So anyway, next section, we're moving into severe weather meteorology and the science behind that. So severe storm defined, what is it? First, hail, large hail with greater or equal to 1 inch in diameter, damaging winds 58 miles per hour or greater, or of course a tornado. Those are the three definitions of a severe storm. You have one of those things, the storm officially becomes severe. And when do tornadoes strike, specifically tornadoes strike in Colorado? Typically, we're getting into May now, so May and June are typically our biggest months as far as tornado count. And then typically, in the mid to late afternoon is when we see most of our tornadoes. We can see them after dark, but typically mid to late afternoon and into the evening hours. And thankfully, most of the tornadoes all over, but especially Colorado, are pretty weak. There hasn't been any EF4s or EF5s reported in Colorado as of yet. However, that doesn't mean they didn't happen, they just haven't been reported. So don't assume that Colorado will never see an EF4, EF5 tornado occurring in the state. It's just they haven't been reported. So something to keep in mind, that they, despite none of them being reported, they still are possible. And we do use a tiered approach of National Weather Service products. First thing, a couple days out, up to a week out, depending on how confident we are in a particular event. And the Storm Prediction Center will issue severe weather outlook with different ratings: marginal, slight, enhanced, moderate, or high risk. That gives you a broad idea of which areas are at most at risk of seeing a severe thunderstorm on a given day. And then as the time approaches, typically the day of, forecasters at our office, at offices all over the United States, will collaborate with the Storm Prediction Center to issue a severe thunderstorm or tornado watch for a given area. So it goes from a bigger scale to a relatively small scale, and then finally to the small. Which is of course the warning. As you can see here, typically smaller than a county. This particular one went into both El Paso and stretched into Pueblo County, but gives you an idea of the different scales as we approach the event happening and the storms happening. And in between there, you know, with the outlooks and that, we generally know which days will support severe weather, including the supercell thunderstorms, which carry the most deadly form of tornado. So we'll start, like I mentioned in the previous slide, we'll start looking at ingredients days in advance, you know, start preparing for what's happening and start getting that message out. And then as we get closer and become more confident, more and more, you know, we fine tune the scale with watches and warnings and such, and try to get that message out to you so you're prepared and can take action. And just a brief overview, watch versus warning. Basically, watch is a preparation stage. When we issue a watch, that's a good time to get ready, know where your emergency kits, that kind of thing are, be ready to take action if something occurs. And warning is, of course, the action stage when we issue this. Typically, we try to get as much lead time as possible, but once a warning is issued, we want you to take action immediately to the different safe places, which we won't cover in this advanced course, but if you were at the basic, you should remember those safe places and where to go. Another funny way to look at it, watch versus warning. Cupcake watch, you have all the ingredients, but it's not ready. Cupcake warning means get in my belly. I'm hungry, get in my belly. So just I like to show this just to give it, you know, put it in a different perspective to hopefully get the idea across to everybody. So several years ago, with the warnings, we switched from county-based warning, as you see on the left, to more specific storm-based warning. And this is just to get the message, the warning out to the right people that are in the path of the particular storm that might not, versus those that aren't in the path and that won't affect or likely won't affect. So we don't have to overwarn and cry wolf, so to speak. So we've shrunk our warnings to be more storm-based instead of county-based. So where can you go to monitor data? The Storm Prediction Center is a great location for a lot of information that you can use if you're like those of us that work at the Weather Service. Of course, we're big weather weenies, weather nerds, so we like to look at this stuff. But you can look at anything from any part of the country. It doesn't have to be just here in Colorado. The website is up there for you. There are several links on the page. The ones on the right highlighted here will have watches, mesoscale discussions, outlooks, fire weather discussion. So there's a number of things you can look at. So if there's any watches across the country, you can click on that watch. It'll bring it up, show you where it is. It'll have the discussion with it. What, you know, if tornadoes, if they're expecting tornadoes, how many, that kind of thing. So it's a lot of good information there with that. And there's some other tools right above the main map. Not only can you get the convective outlooks, watches, mesoscale discussions, but you can also look at any storm reports that came in that day. What's called the meso analysis, which is a small area that will get into a lot of details with the different products that you can look at, which I'll get into in a little bit later. I've got that coming up in a few slides. And then as well as fire, and then all hazards with the National Weather Service. And then there's also, if you're into forecasting, there's a forecast tools option in the top center of the page. You just click on that, and then this next page comes up with all kinds of different forecast tools as well as observations. The top one is the upper air maps. These maps and derived fields are based on weather balloon data and radio sound data. So this will tell you, will give you an idea what the upper air looks like and where you can expect possible unsettled weather or nice weather, that kind of thing. Just gives you an idea of the pattern across the U.S. Then there's also, in the observed sounding, there's SKYWARN charts from the actual radio sound data. And that'll tell you CAPE, SIN, other parameters that we look at for severe weather. And we'll get into CAPE and SIN here after a little while, then a few slides, but you can look at soundings from across the U.S. here as well. If you're looking for something to do on a Tuesday afternoon or something like that. And again, like I mentioned, there's the meso-analysis maps with several derived severe weather parameters that you can look at to give it an idea of what's happening in the next couple hours as far as severe weather is concerned. So what weather patterns associated with severe storms? First thing we look for, what are upper troughs and upper ridges. So we look at the upper atmosphere, the different layers for this. And this yellow dotted line kind of gives you an idea what a trough and a ridge looks like. As you can imagine, a trough looks like a horse trough, and then a ridge looks like a ridge. So typically under the trough, there's going to be colder air, and in between there's going to be a low pressure system at the surface. And also associated with this transition between the trough and the ridge, there is what's called typically a low level jet. We do see those here more so on the plains of Colorado, but even more so a little bit farther east. But this brings typically the southern, a little bit stronger wind will bring in some moisture and warm air. It'll bring in some warm air, which helps destabilize the atmosphere out ahead of the cold air and the developing low pressure. And there's also a couple of upper jets. There's a polar jet, which is a jet streak that's more to the north, and then a southerly jet, which is a jet streak that's a little bit to the south. And this will help, as well as this will help provide lift depending on how strong it is and exactly where it's located, and will help out with shear as well, which we'll get into in a little bit. And then all this process as well will bring a warm sector to the area, and this warm sector is typically where the most severe weather is going to occur, in that warm sector with warmer temperatures, warmer dew points. So moving on into ingredients for severe weather, there are 4 main ingredients that we look for: moisture, instability, lift, and wind shear. And we'll get into those as we go along here. The first ingredient is moisture. Typically, the low-level moisture will come from the Gulf of Mexico. And then out to the west here with the mountains, we get dry air that comes in and they clash in the middle. But some of that moist air is able to come up all the way west to the mountains. And here, especially in Colorado with a higher elevation, you get around a 50 to 55 dew point, 50 to 50, I should say, brings the capability for supercells and even tornadoes. But when you get into the central plains, a little bit lower elevation, then you do want to see higher dew points to get tornadic supercells to occur there. But seeing we're higher elevation, it doesn't take quite as high dew points for supercells to occur, or tornadoes for that matter. So the next, I know that was pretty brief about moisture, but moving on to instability. For an unstable air mass, you typically want cooler air above, warm and moist air near the surface. That allows air parcels to rise and continue rising and blossom into a thunderstorm, and if strong enough, into a severe thunderstorm. So what is it? Where does it come from? The atmosphere is unstable when air is displaced upward and continues to rise. If there's nothing there to, in other words, if there's nothing there to stop that air from rising, that's what's considered unstable. So some mechanisms for increasing instability: warming near the surface, moistenings near the surface. So if we have some moisture coming in from the Gulf of Mexico, or some warmer air as well from the south, cooling aloft, that allows parcels to rise even faster. And if you ever heard of the cap, we use that term quite a bit in the weather realm, I guess is the right term. The cap is basically what stops the potential instability from being realized. So there might be a little more layer of warmer air in between the warm air at the surface and the colder air aloft, which would stop the air from rising. And that's why it's considered the cap. And then the CAPE, the convective available potential energy, is the most well-known index. For you weather nerds out there, you've probably heard that term several times, especially if you're into severe weather like myself. And one thing we use to determine all that is called the parcel theory, which we get that from the atmospheric soundings that I mentioned earlier, and we'll get into that here in a little bit, how we use that. In fact, we'll get into it now. So parcel theory, with the SKYWTs, the soundings, we'll show you that too in a little bit. So with this theory, consider imaginary balloon of air that you have outside. And as we know, cold air is denser than warm air, so warm air rises, cold air sinks. And as this balloon is nudged upward, whatever might be nudging it upward, it cools at a constant rate, but the environment around it might not cool at the same rate as that particular balloon as it gets lifted. So if that balloon continues to be warmer than the air around it, it will continue to rise. If it's cooler, then it'll go back and sink back down towards the surface. And the other thing we know is dry air cools more rapidly than moist air. That has to do with a couple things. Release of latent heat with the moist air, as well as the specific heat of water is quite high. So the more moist the air is, the specific heat, what that means is how much energy it takes to warm something 1 degree. So as with more moist air, it's going to take more energy to warm that up. So it and it also cools slower as well. So so that is why dry air is able to cool faster than moist air. And soundings will also illustrate this very well, as we'll see here shortly. And here's a couple of soundings with actual weather balloon data. On this gives us the temperature of the environment. In here, there's a lot of stuff going on here. I understand that. Hopefully follow along here, but the temperature and dew point of the environment. The temperature of the environment is the red line there, and then the dew point is the green line. So we can figure out the temperature of a bubble of air as it rises. It will cool along what's called a dry adiabat. There might be kind of hard to see, but let's see if I can point it out here. So this yellow line down here goes along the dry adiabat. It's kind of hidden by the red temperature line. But then we know the dew point at the surface, in this case the mixed layer, and the amount of moisture stays the same, so and that rises as well. So that's why that kind of makes an inverted V with that white line. But when they meet, they become saturated and then rise along a moist adiabat. And whenever that yellow line is to the right of the red line, we'll get what the cape is, which tells us how much energy there is available. And in these two instances, on the left here, we see short fat cape, and then on the right, we see what we call long skinny cape. And typically, a short fat cape will give us a little bit more energy, so the updrafts can rise faster than something here on the right with the long skinny cape. This will be a little bit, it'll still rise quite high, but it'll just be a little bit slower. It won't be quite as vigorous as the sounding here on the left. And I know that was a lot of information. Going in, now we're going to give you folks a little test here. So stable versus unstable. So in this situation, we have warm air over cool air, and we have this bubble of cool air form right above all these houses. So will a balloon filled with cold air rise in this situation? And go ahead and answer the question. We're getting a good number of responses and starting to plateau, so give it just a few more seconds here. All right, as we can see, there was 90% that voted no and 10% that voted yes. So let's see what happened. And yeah, the 90% were correct. The balloon will fall in this instance. And this is what's considered a stable atmosphere, as we described earlier. This illustration is just a little bit, helps, again, illustrate the process, stable versus unstable. So now we got another situation. Now we have cool air over warm air. And now will this balloon rise? Give you a second to look at the image here before I start the poll. Voting starting to plateau out here, so I'll give it a couple more seconds. Alrighty, this time same ratio, but just the opposite. 90% said yeah, the balloon will rise. 10% said no, it will sink. So let's see what happens with this one. And yes, this one does rise. Again, cool air over warmer air. Warm air is more dense, so it's going to continue rising. So this is considered an unstable atmosphere. So nice job, everybody. So just a recap of both sides. Stable is when you're going to have warm air over cool air, and the balloon, quote unquote, will sink. And then unstable, cool air over warm air, that balloon will rise. And one key to this is remember that cold air is more dense than warm air, so it tends to sink when it comes in contact with if a cool air runs into warm air, it will sink. So now getting into the cap, hopefully this illustrates better what I was talking about before. So here we have a layer of warm air at the surface up to a certain height, and then a little nose of warmer air in between that warm air and cool air. So here, if we have the bubble of air, it starts to rise, whether it's nudged up by a front or whatever the case may be. But as it rises, once it encounters that warmer air, if you remember, cold air is more dense, so warm is still colder than warmer, so it will stop there or maybe sink, and that prevents, a lot of times the cap occurs and prevents storms from forming, but there are things that are able to break the cap if fronts are strong enough, that kind of thing, or it gets warm enough at the surface finally, that cap can erode and become unstable instead of capped like it is here. And another term for the cap is called convective inhibition, or SIN. And this, as the name implies, it inhibits the development of convection. Again, as you can see in the sounding here, let me pull up my pointer. Down here near the surface, we got a little warm nose on the sounding. So this, until the temperature rises enough or something strong enough that pushes the air past that, that's going to block any parcels that are rising from breaking through and getting a hold of this CAPE, the potential energy. So just because it's potential energy doesn't mean it's going to be realized, something to keep in mind as well. So again, the convective inhibition is the same thing as the cap. So if you hear someone call it the cap or convective inhibition or SIN, we're all talking about the same thing. So three-dimensional atmosphere instability. Again, hot surface, cold air aloft. This is where the fatter CAPE comes in that I was showed earlier. If you have a hot surface and warm aloft, it's a little bit thinner. So these on the left, the CAPE values are typically greater than 1,000 joules per kilogram, and on the right, the CAPE values are less than 1,000 joules per kilogram. So the greater the CAPE, the stronger the storms can be, the stronger the updrafts can be, which can produce obviously more stronger storms, more severe storms, so on and so forth. And this, again, just because this CAPE is there doesn't necessarily mean it's going to be realized. So this, but we do look at this and use this as an idea of what kind of storms could happen if they're able to tap into that CAPE. And how do you monitor instability? Again, the SPC page is very good. This is that meso analysis page, or mesoscale analysis. And there's so many different parameters that you can look at here. As you can see on the top bar, all kinds of different options. But the key ones are thermodynamic data. These are ideal for instability analysis. Most often we use CAPE or mixed layer CAPE. And then we'll also use different indices to help us determine the severity index for that particular day, like the lifted index. This one is more negative, the more unstable the air mass is. We'll also look at low and mid-level lapse rates to give some idea of hail potential, which is our main threat here in Colorado, of course. And those lapse rates of 7.5 to 8 degrees Celsius per kilometer do indicate a severe hail threat. LCL height is another one. That's a cloud base height. The lower the cloud base height, typically the better chance of a tornado occurring, especially from a supercell. And a bunch of other fields that you can monitor to determine what kind of storms might form that particular day. And here's just a zoomed in list of all of the things I talked about, plus a number of other options that you can look into. Again, it's a lot of cool stuff to look at for those weather nerds like myself. So what does instability in discussions look like? I have a few examples here. Here's a mesoscale discussion from back in 2014. Just highlighted some terms that they used, like destabilize, negligible, SIN, modest instability. And then getting a little bit, another option or another area to look at it is in the convective outlook. And here, so this is the slight, enhanced, moderate, outlooks. Here they used amply unstable air mass, and it might not be as direct as that. For instance, here, background kinematic and thermodynamic environment, supportive organized storms. So that, even though it doesn't say instability directly, it wording like that indicates there is instability in the atmosphere. And then finally, even on a local scale, point blank, they say instability, or even something like environment remains very favorable. So if you're looking at forecast discussions or convective outlook discussions anywhere in the US, these kind of terms will show up if there is instability in the atmosphere. So something to look out for if you're into reading these kind of discussions, getting into the more technical information from forecasts. So the last ingredient for storms, not severe weather, but the third ingredient for severe weather is lift. And that's just something that gives the air a nudge upward, whether it's fronts, cold and warm fronts, dry lines, outflow from other storms, which can generate a thunderstorm itself. Just outflow from one thunderstorm can generate a thunderstorm just based off of that outflow, or even just enough heating throughout the day, it can warm up enough to overcome that cap we talked about earlier. So looking at 3D views of a warm front and a cold front, the top one is a warm front. As you can see, the cold air here is the passive air mass, so it doesn't do a whole lot, but because it's more dense, the warm air still rises over it slowly. So a lot of times this will be rain events, but there typically is more circulation related with warm fronts. So there can be, this is an area to watch out for, especially closest to the low pressure near the surface. It's an area to look out for tornado formation if a storm can form by itself outside of everything else. And then a cold front, this is where the cold air mass is more active. So it's actively pushing the warm air out of the way. And this is a lot of times when, so the air rises a lot quicker typically and can form more vigorous thunderstorms, providing more opportunity for severe storms and such. Another possibility for providing lift is convergence at the surface. And typically this is seen through fronts, but it doesn't always have to be associated with fronts, but you can have even small scale winds and two coming in opposite directions, so they come and converge with each other, and that will, seeing it doesn't have anywhere to go but up, that will give that air a little bit nudge to help it rise and form new thunderstorms possibly. And the fourth and final ingredient for severe weather is that wind shear. And wind shear, definition of that is winds that increase and veer with height, as the diagram shows. Might have south or southeast winds at the surface, but as you go up in the atmosphere, they'll turn more to the west, so it allows for rotating storms and such. The key with this is it tilts the updraft, which separates that updraft from the downdraft, which allows the storm to survive and keep gaining strength without just being a typical garden variety thunderstorm. And this wind shear also supports rotation, like I mentioned a little bit ago. Now we'll get into the the granddaddy of them all, the supercell. We'll get into the meteorology of this. What we got? All right. Oops. All right, so supercell thunderstorms are responsible for virtually all deadly tornadoes in Colorado as well as the United States. For the tornado likelihood, we'll look at low-level moisture. Abundant low-level moisture results in higher instability in the low levels. So this supports stronger and more persistent updrafts than drier air at the surface. So southerly or southeasterly winds across the southern plains transports that low-level moisture, like I mentioned earlier, typically from the Gulf of Mexico is where most of our low-level moisture comes from. And then low dew point depressions, or the difference between the temperature and dew point, are better for lower cloud bases, which I mentioned before, or LCLs, which I mentioned before is good for tornado formation. Having the lower cloud bases is good for that. And there are 3 types of supercells. On the left is the low precipitation supercell. This one, as the name implies, there's very little or sometimes not even any precipitation from it. But they are very, very pretty, but they're still very dangerous. There's still a lot going on that could cause a lot of issues. The classic supercell, this is where a lot of times when you see gorgeous pictures of tornadoes, for lack of a better term, out in the middle of nowhere, hopefully. This is typically the supercell that you see with rain off to the northeast a lot of times. And then finally on the right is the high precipitation supercell, which typically this is the most dangerous because if there is a tornado, it's going to be wrapped in the rain, and making it very, very difficult to see. A lot of times you won't even see a tornado in these situations. And looking at the nuts and bolts, there's a lot going on here. I'll do my best to explain everything in the next several slides here. But the critically important feature that I'll mention on this slide is what's called the mesocyclone, or rotating updraft is another name for it. So this is what makes a supercell. Without this rotating updraft mesocyclone, then it's not considered a supercell. And as you can see with everything else, flanking line, anvil, mammatus, forward flank downdraft, so on and so forth, there's a lot going on with these single thunderstorms. And this is a big reason why they're most dangerous. Looking at an overhead view, again, apologize, I had to take another drink of water. We see the highest reflectivity just to the northeast of the updraft in this case. And there is where we'll typically see the heaviest rain and hail. Sometimes that, again, in high precipitation supercells, that rain can move around, get pretty close to the updraft, or in high wall clouds, tornadoes, that kind of thing. Out in front of the storm, we have the forward flank downdraft caused by the evaporation of rain as it cools, falling towards the ground. Then also rear flank downdraft towards the back, which we'll get into both of those a little bit more here in the next coming slides. And there's also the inflow going into the storm, which provides warm, moist air to the main part of the updraft to keep it surviving. And Speaking of the updraft, it is the most prominent feature. The vertical motion in these updrafts are extremely strong, very fast, can reach 100 miles per hour or greater, and can grow over to 60,000 feet in height. So if you think about it, most planes fly about 30 to 40,000 feet. So these thunderstorms are another 20 to 30,000 feet above that, where the updrafts are anyway. If you look at them, you can see that they are tilted. Again, that's due to the wind shear. And then a large anvil tilts into the upper level wind. So that's a good indicator of which direction that storm will most likely go. Not always, but gives you an idea, especially the upper level winds. That'll tell you which direction those are. And often, because of that strong updraft, it will have an overshooting top, as you can see in the top picture there. And some of my favorite clouds, or one of my favorite, are the mammatus that you'll see underneath the anvil out on the front part of the storm. And sometimes you'll see striations like you see in these couple of videos. Not sure how quickly they're showing up for you guys watching at home. But even a still picture, you can see the striations in the updraft. And this indicates very strong rotation in a mid-level cyclone as well. And typically precursor for large hail, damaging winds, and even possibly tornadoes. And just to go over, I know we covered a little bit about the mesocyclone already, but it is a rotating thunderstorm updraft. Again, the main thing that makes a supercell develops actually first in the mid-levels of the storm, and then transfers to the low-level storm or expands to the low levels under the right conditions, and varies in how they look, from barrel shape to barber pole shape, you get those striations like in the bottom left, but these are not always visible in the higher precipitation supercells. So how do they form? First, ambient shear, so the different winds changing with height, creates a horizontal vortex or a tube of rotating air that's moving horizontally or oriented horizontally. Then it interacts with the updraft of the thunderstorm that's going overhead of it, and that tilts it into the vertical. And then as the updraft intensifies, that rotating column is stretched, causing to spin faster, and then the mesocyclogenesis is complete. And so we like to use big words in meteorology, so that's why we use words like mesocyclogenesis. And getting into a little bit more of the intensification, initially we'll have a weakly rotating thunderstorm, and persistent rotation is supplied by environmental shear and ingested via the forward flank downdraft, which we'll show that here in the next couple slides, give you an illustration of what that looks like. The rear flank downdraft supplies additional buoyant air to the updraft due to the warming air that's sinking from it, which we'll get in a little more into that here shortly. Then the updraft intensifies from that, stretching out. And if you think of an ice skater, as they make themselves skinnier and taller, they rotate quicker. So it goes from, if they have their arms out, they rotate at a certain speed, and then as they bring their arms in, they're able to spin a lot faster. So think of it that way. As it gets stretched like that, the updraft, it's able to rotate quite a bit quicker. So getting into More detail about the forward flank downdraft. It occurs on the leading edge of the supercell and is normally offset from the cloud base. As you can see in the upper left picture there. So yeah, not the mesocyclone itself, but out ahead of it, not where the updraft is. And as you can see in the radar image there, it's outlined where the forward flank downdraft is. This can contain blinding rain, damaging winds, and large hail. As well as you can see shelf clouds from this. And depending on where you're at, it can obscure a tornado if there is a tornado on the ground. This FFD can obscure that depending on, like I said, depending on where you are. Rear flank downdraft may contain sustained winds over 100 miles an hour and hail larger than baseballs. So this is a very dangerous part of the storm. And how you can identify it by the updraft or where the tornado is, just behind it, you can see a clear slot. And sometimes because of the strong winds, depending on the strength of the tornado, this can cause more damage. The wind from this can cause more damage than the tornado itself. And it develops in response to the pressure patterns within the thunderstorm, which we'll touch on that here in a little bit. Again, the clear slot develops as warmer and drier air evaporates the cloud debris and sinks towards the surface. And then tornadoes typically north of the rear flank downdraft in the clear slot. Sometimes though, like I mentioned in the last one, you can witness a clear slot, but they can be wet as well, which will contain rain or hail. Again, could be very large hail, baseball size. It can be warm or cold, and if it is warm, it's often associated with tornado formation. If it is cold, it is often unfavorable for tornado formation. As you can imagine, the warm air, like it says, is more unstable. The cold is more stable, so it's going to, depending on what it is, will enhance it or kill it off. And sometimes, of course, I can have a little bit of both. So how do they develop? Well, and this diagram shows it a little bit. It's very complex. They originate in the mid-level, with the mid-levels winds entering the storm. Lower pressure near the surface due to the storm and the processes that are going on with it drives that buoyant air downward, because pressure in the middle is going to be higher pressure, and air wants, like any fluid, wants to go from high pressure to low pressure. So it's going to head in the direction down towards the ground. And because of that pressure difference, and then that compression causes a warming and drying, and a lot of times that's why we get that clear slot I talked about earlier. So in this illustration on radar, we see mid-level air enters the storm right here, just near what's called the hook echo, out ahead of it a little ways. We can see that very strong gradient between the different reflectivities. It's green and then quickly goes yellow, orange, and then red. So that's where the mid-level air enters the storm and then moves downward toward lower pressure, like I mentioned before, warms and dries. And then that's how the rear flank downdraft is born. It partially what forms that hook echo that we see in that image there. And one last bit here, I believe it is anyway, on supercells and the different components is the flanking lines, which are a series of a line of cells merging into the main storm, and often it'll be to the backside of the storm, so to speak. This allows persistent source of updraft energy to the storm. So if you see these, typically it will promote longevity of supercells, keep them going, keeps feeding them. So as maybe the main updraft starts to weaken a little bit, it's got these sources of energy to help feed it. And again, like I mentioned, it's on the backside, so it's on the south or southwest flank of the storm, typically. And these are most common in cyclic supercells. The cyclic supercells are the ones that produce tornado after tornado after tornado, produce a tornado, and that tornado will die and then recycle and produce another one, so on and so forth. So if you see these, typically that means it's that storm could last quite a while. And as the illustration shows, provides energy into the updraft. So from supercells, one of the main threats is hail, and it's the most common threat here in Colorado. And typically does fall away from the updraft, but not always. Sometimes it does. Sometimes it does fall out of the updraft, but typically not. And can range in size anywhere from 1/4 inch to several inches in diameter. And in fact, if you saw the basic spotter talk that we gave a couple weeks ago, we showed this there as well. But the world record hailstone happened in South Dakota, which is 8 inch in diameter. So you can imagine how hard that would hurt if it hit you. Definitely would tickle, if nothing else. How does hail form and how does it get so big? Well, in the storm, there's going to be a freezing level, and as raindrops form and get ingested in the updraft, they're pushed up into the freezing level, so they freeze and eventually get out of the circulation of the convection currents in the storm and start to fall down again, and sometimes drop below the freezing level, sometimes not, but then it'll get sucked back up into the updraft and then is able to grow a little bit more, and then that pattern continues for a while, and then depending on the strength of the updraft will depend on how big the hail can get. And once it gets too large for the updraft to sustain it or keep it from falling, it'll fall out and hit the ground. And as you can imagine, some of the updrafts for like the 3 inch hail or that 8 inch hail must have been extremely strong for it to keep growing like it did. Next part of the storm talk that we'll talk about is the wall cloud. This is typically the quote unquote action part of the storm. It's where the strongest updraft or lift is in the particular storm. And this is where storms normally develop, tornadoes normally develop. Sorry about that, neighbor's dog is going crazy. And it also might be accompanied by a tail cloud in very moist environments. But again, with the HP, the high precipitation supercells, it may not be visible at all. And this, again, that's the most dangerous type of supercell. And something to consider is just because there's a wall cloud there does not mean it's going to rotate. Not every single wall cloud rotates. Of course, the rotating wall clouds are going to be the more dangerous one. And How do wall clouds form? Well, first, again, you have that warm, moist inflow coming into the storm. And then the cool outflow from the forward flank downdraft region. That cool outflow and moist inflow allows the air to condense and form cloud droplets. And where those meet is where the wall cloud forms. And in certain situations like this particular one, there is a tail cloud that may form along the FFD if enough low level moisture is present. So again, what's the difference between wall cloud and shelf cloud? They do look very similar to the untrained eye, but something to consider, or if you're wondering if it is a wall cloud or shelf cloud, typically the shelf cloud is going to be out ahead of the storm, as in the top picture. And something to remember is the cloud typically points down towards the ground, points away from the rain, whereas wall clouds here on the bottom typically will point towards the rain. So if it's the shelf cloud is going to be out ahead of the rain and wall cloud is going to be behind the rain, and so the shelf cloud points away, wall cloud points towards. So something, if you're out storm spotting, you see this, those are just some quick keys to consider while you're looking at that. And of course, the tornado, the most damaging part of, or can be the most damaging part of the storm. Depends on how strong it is and how long it lasts. Sometimes the hail is more the issue, but these can last from a few seconds to over an hour, can travel a mile or less to over 100 miles, and then they can vary in width from tens of feet to over a mile. One of the tornadoes in the southeast just might have been Easter or might have been later, I can't remember exactly when, but there was one that was reported over 2 miles wide. So they can get very large, very destructive, and as a result of extremely sensitive and complex set of conditions that come together on rare occasions. And how does that happen? Well, unfortunately, it's still very poorly understood. Still a lot of researchers studying the tornadogenesis. One possible theory is there's an intense area of low pressure that develops below the wall cloud of the storm. And then surface convergence increases as updraft within the mesocyclone intensifies. And then condensation occurs as rising air saturates within that inflow where the green arrow is pointing in the downdraft from the storm interface, whether it's the forward flank downdraft or rear flank downdraft, and tornado develops from that. Again, that's one possible theory. It's not well understood. So I just wanted to bring up that particular theory just to give you one option or one possible way that they form. But again, it's not well understood of how they are formed totally just yet. And some of the stronger tornadoes can have multiple vortices. And this is due to a force imbalance within the tornado, or in other words, friction. So in tornadoes, like I mentioned, or in storms, like I mentioned before, there's higher pressure within the storm in the mid-levels and low pressure at the surface. And then that low pressure in tornado becomes extremely low and remains there. And then again, high pressure flows from the high pressure to low pressure and causes the tornado to widen as there's more air coming down. And once that core downdraft reaches the ground, multiple vortices form to maintain that force balance. Those physics fans out there, one thing you learn is force is always in balance, so there's something that's got to, some forces, some types of things that's got to keep forces equal, and that's how nature does it in this case. Is the vortices are formed to maintain that force balance. And again, these are typically associated with the strongest tornadoes. Wind speeds much stronger in suction vortices than single vortex tornado. So the wind speeds with these are going to be a lot typically stronger than a single vortex tornado. In some cases, like what happened in El Reno, Oklahoma back in 2013, secondary vortex breakdown may occur. So that tornado was 2.6 miles wide, I want to say. It broke down into multiple vortices. Some of those vortices inside there were large enough and strong enough that even more subvortices formed within those. So it's pretty amazing that that can happen. Looking at more the non-supercells or land spouts, as they're commonly occurred, or one of them is a land spout. These occur again from stretching the environmental vorticity along a front or boundary, and normally associated with higher base storms, where the supercell tornadoes are lower base storms that produce those. Even though these are typically weaker, they can still get strong enough to produce damage, depending on where they occur, of course, but they can produce damage. And other things that spin, one is a gustnado, and more like a strong dust devil. And these are circulation that forms along thunderstorm outflow, as this diagram indicates, and can cause minor damage, but usually not that strong, but sometimes they can cause damage. And this is a video, I hope it shows up well for you at home, but this is a video that I took just north of Pueblo last summer sometime, showing a gustnado. And I apologize, it does look like it was pretty choppy for you folks at home, so I apologize, but anytime you want to see that video, just let me know. So safe, if you do come across a supercell, safe positioning, obviously we want you to do that. I got one more quiz question for you here. We'll make it quick though, because we're running out of time already. I apologize for that. So with this, group A is in the northwest part of the storm. Group B along the front edge of the storm, basically, or group C down here ahead of the storm. Which do you think is the safest position of these three? Again, A was in the northwest part of the storm, B is out in front of the storm, or the front part of the storm, and C is just to the south of what looks like a forming hook echo. All right, looks like pretty much stop receiving votes. So 52% said position A, 9% said position B, and 40% said position C. So position A is not good, nor is position B, but position C is typically the best place. Of the three options that were given, it gives you a good chance to see where the tornado is if it's not rain wrapped. Where the other two, you're going to be in heavy rain, can't really see anything, and not sure exactly where things are going and what could hit you as far as, you know, hail, that kind of thing. So the A and B in the northwest, and then the east side of the storm, not so great, but C would be the best area to be. Gives you a quick escape route as well if you're in that situation. And sometimes supercells can split. One, and they'll split into two. One will go off to the left, one to the right. As you can see, left split and right split. Left split typically produces very large hail, but rarely produce tornadoes. Not never, but rarely. And then the right split usually moves fairly slowly and more likely to produce tornadoes, but also can produce large hail, not just the left movers or left splits. It's supercells. Again, as far as positioning goes, splitting storms presents a challenge, with left movers being notorious for massive hail. They'd be in a definite, that pink X there is in a not necessarily a good situation. And the right movers may turn southeast or even south-southeast. So even the red X there could be a dangerous spot, even though in the last slide you said it was the better of the three. So you just got to be very cautious of which way the storm is moving. And the nice thing about the red X is you do have an escape route in that instance, where the yellow X, again, in the heaviest precipitation, not necessarily a good location. So communicating damaging wind and tornado threats in our warnings. We covered this in the basic training, so I'll go over this pretty quickly. Again, thunderstorm wind hazards don't fit neatly into boxes like tornado strengths, you know, EF 0, 1, 2, 3, up to 5. Straight line winds can be a number of things, as this list here shows. Again, I won't list each one of them. And they can reach very strong, over 100 miles an hour at times. So they can still do quite a bit of damage, even though they're not tornadoes. And then deciding on what type of warning to use, a severe thunderstorm versus tornado. We look at a number of things. As you can see here, there's a number of products that we look at, radar product, satellite, bunch of other products, environment, and we just take it as a whole and use the preponderance of the evidence, as we like to say. Again, the key is knowing the environment that the storm is in, and then a number of other things, radar data, reports from spotters, storm history, has it produced a tornado before, has it not, damage potential, and duration of the storm as well. So there's a number of things that go into deciding to go with a tornado warning versus severe thunderstorm warning. In our warnings, we try to communicate the different threats with the different warnings. With severe thunderstorm warning, we can have a base one or one with elevated wording, depending on the size of hail, wind strength, or if we think we're not quite sure there's a tornado, but we see rotation with the storm, we might put a tornado possible in it. And the tornado warning, we'll use radar indicated observed from a spotter report, considerable if we have indication is a very strong one through radar data, or catastrophic and these are very rare, but if these go through a populated area, then we'll issue those types of warnings. And quick reporting refresher. Just remember 3 C's of emergency communication: clear, concise, and calm. So yeah, just remember those 3: clear, concise, and calm. And here's an example of a good report. You want to give us your name, your exact location. If you're at the intersection of 2 streets, that'd be great. And that way it's easy to find you on a map. Describe what you see, but be as brief as possible, because during severe weather, we're getting a lot of calls, so we want to get as much information in a short amount of time as possible. Where did you see it? If it was right at your location or in a certain direction from where you are, and a rough estimate of the distance away. And try not to get confused. I know that's easier said than done, but yeah, just do your best to not get confused. And then when did it happen? Did it happen right? Is it currently occurring? Did it happen 5 minutes ago? Whatever the case may be. Then what to report? Hail, anything penny size or larger. Severe thunderstorms require a hail of 1 inch diameter, so that's why we put the penny size 3/4 of an inch or larger. Gives us an idea how close to severe that storm is, and maybe it's producing larger hail in some spots. And just a reminder, do not report marble size hail. They're coming all different sizes, so we don't know what size you're referring to when you say marble size hail. And winds, anything 58 miles per hour or greater, if you have an anemometer, or damage caused by thunderstorm winds, including large tree damage, or if you have the roof blown off a house, those types of things, those are what we want you to report. Winds of like 30 miles an hour, not so much with lighter winds like that. Not that 30 miles an hour is necessarily light wind, but not quite severe. And a rotating wall cloud is another thing to report. Which is the lowering of a rain-free base, look for that persistent rotation. And a rapidly rotating wall cloud often precedes tornado development. And funnel clouds are another thing you want to report, which can be confusing. In the basic, we went over some lookalikes, but this one, this advanced, we won't discuss those, but just make sure if you see something that looks like a funnel cloud, make sure it is rotating. And then of course, tornadoes. We want to report tornadoes. And as the middle picture here shows, a tornado the condensation funnel doesn't need to be in contact with the ground. As you can see, the middle picture, there's no condensation funnel there, but there is debris being picked up. So that's when you know it's a tornado. So that's what you want to report. And best ways to report severe weather to us. Could it hurt or kill somebody? If yes, best way to do it like a tornado, damaging hail, wind, dangerous flooding. You want to call us on our phone number, which is on that hail card. If it probably couldn't hurt somebody, other avenues such as spotter network, amateur radio, online forum that we have, Twitter, Facebook, email, just kind of a broad decision tree there for you to use. Again, phone call, dial the 800-884-1540, what weather you witnessed, where it was, and what time it happened. Again, that number will be on the hail card coming up, so don't need to memorize that. But always remember safety first, and follow all traffic rules, while you're out and about. And very important, respect private property. Don't want you to be going on someone's property to take a picture of a storm or grab a hailstone, anything like that. Just be respectful of other people's property. And a couple of plugs for data. If you have an internet connected weather observing station, you can join the Citizen Weather Observer program. This allows us to get more data into our database, which will help us provide better forecasts, and we continually want to improve those. So I'll leave this slide up here just for a few seconds. If you do want to join, there's a website down there in the bottom right corner. Just go ahead and take a picture of that, and if you're interested, if you have a weather station, go ahead to that link and you can sign up to have the National Weather Service use that data. And I believe you can still use that link if you're not in our county warning area, still want to sign up for it. Let's say you're in Northeast Colorado or somewhere else, feel free to sign up, and we would love to have that data available to us. And another observing network that we use the data from is called COCORAS, or Community Collaborative Rain, Hail, and Snow Network. This is mainly precipitation, but you can sign up for this as well. And this is just a picture of the main the homepage of the website. And the website's right there, cocoras.org. Go ahead if you're interested, sign up with that. If you like taking rainfall measurements every day, it's a great way to help out neighbors and us as well with precipitation and getting that ground truth out there as well. I'm getting down to the last few slides. To help us build a weather-ready nation, have a plan in place for you and your family. Encourage your friends and neighbors to do the same. Prepare those emergency kits, have a weather radio in your home and office, and review your insurance policies. And your business can become a weather-ready nation ambassador. And the ambassadors promote weather safety, coordinate with us on potential collaboration opportunities, educate employees on workplace preparedness, and also share your success stories of preparedness with other people through social media and different avenues as well. So just a reminder, before the storm, have a plan, know your risks, and practice that plan. All right, so here's the certificate passwords, both for the certificate and the hail card. If you want to take a picture of it here, go ahead. I'll leave it up here for a few seconds, but I do have it on the last slide, which I'll leave up when we're answering questions. Okay, and to get that certificate and hail card, you go to our spotters page, which is weather.gov/pub/spotters. Or if you just go to weather.gov/pub, there'll be a link for online spotter talks. You can click on that and it'll bring you to this page as well. And then you'll want to click on the certificate hail card tab, enter your information there, first, last name, and then the date that you attended, which would be April 27th. And then enter the password on the last page that was on the previous page and hit submit. And then a certificate will pop up ready for you to print. You just click on Hail Card Access. It'll ask for the password, which is the same thing, and then you'll be able to print off that. So again, like I was right there, that was the presentation. Hopefully you're all still awake. I appreciate your attention. Couple of emails. If you have something that you want to discuss after this, direct emails, or if you have just a general question, you can also email the main office email, which is nws.pueblo@noaa.gov. And then there's the number as well, the spotter telephone number to call as well on the bottom. So with that, again, thank you for joining us tonight.